Sorry about that. Me and my technical difficulties. All right, so these three definitions are really important. The problems for KSP can be a little different than the other problems, and it comes into these definitions. I'm not saying they're harder because they're definitely not, but you have to understand what they're asking for. So first of all, let's go through what these terms mean. So the first term we have here is the term solubility. Okay, solubility is referring to the maximum amount of solid that can be dissolved in a solvent. Okay, we've talked about solubility before. And solubility is usually in the unit of grams per liter. Okay, grams per liter is usually the unit. Now, if they use the term molar solubility, and you see the difference here between that term and, now none of my pens want to work. This thing hates me. All right, so you see the word molar solubility. That's the same thing, solubility, maximum amount of solute that can be dissolved, but it's in the unit of moles per liter, hence the term molar solubility, okay? So those two terms are going to be used frequently in your notes, and you need to make sure that you're paying attention to whether or not it says solubility or if it says molar solubility. And again, if you're given units, pay attention to what the units are. Is it grams per mole or liters per mole? Because that is going to be an important aspect. And then the other term that we have here is solubility product constant. That's your KSP. Okay, again, it sounds fancy. Another way to say it would just be the equilibrium expression, okay, because it's the same thing, but they give it a special fancy name, solubility product constant, hence KSP, solubility product. And it's the ratio of the difference between the reactant concentration and how much actual ion solute dissolves. So again, you already know that, right? Your KSP is always your products over your reactants. Well, the only reactant you have is a solid, so KSP is just going to be based on how much ion actually forms. Okay, so let's get into looking a little bit more at those two terms. I want to explain something to you. Before we do that, let's do this problem. This one is unrelated to that. This is just a little bit more straightforward. It says, predict which of the following compounds will have the greatest molar solubility. Okay, so essentially they're asking which one is most soluble. So think about what we talked about before. The bigger the value of K, the more soluble it is. So you want to look through all of these. And although all three of them are not very soluble, look at their 10 to the negative 10, 10 to the negative 13, and 10 to the negative 17. This one right here, sorry, sneezing's back. This one right here must be the most soluble, and it's the most soluble, so we'll just write here, write in your notes, most soluble because it's the largest KSP. Sorry about that. Okay, so if you're asked to decide what's most soluble and you're given KSP values, it's very straightforward. Just find the largest KSP. Okay. All right, now here comes back our terminology. This is so important. You know, you're at home, get something like bright, dark, I don't know, something that makes it stand out. This part right here that I've already bolded for you, but it's so important. In our calculations, our tables that we do, which by the way we're still going to use for KSP, those tables, in those tables that we do, the value of X, when we go through and we find X, we calculate X, you know how we use quadratic sometimes, or we don't use quadratic, sometimes we get to take the square root, whatever. When we find X, X is the molar solubility. Okay, the X value is the molar solubility. It is a representation of how many moles per liter can be dissolved. So if a problem asks you, what is the molar solubility? So if the question is, what is the molar solubility for something, what you're doing is finding X. Okay, that's your job. If the question tells you the molar solubility, okay, if they say the molar solubility of such and such is, 4.2 times 10 to the negative 6 moles per liter, find whatever they want you to find, they've just told you X. Okay, so if they give you the molar solubility, they have given you the X value. Talk about easy problem. They've given it to you. But if you don't know that molar solubility is X, then you will have a hard time. because you won't know how to find X because you'll be confused. So molar solubility is X. Let me show you what these problems look like. Okay, and again, they look a little different, but don't let that intimidate you because, in my opinion, KSP is the easiest out of all of the types of problems. So, first of all, you look at the problem, you may get very nervous. Okay, usually equilibrium problems, most of them, and KSP for sure, you're going to be using an equilibrium table, but you don't have an equation. But remember, they won't give you an equation. Anytime it's KSP, they're referring to a solid dissociating. So don't even read the problem yet. Let's just write down the equation for the dissociation of this substance. So it's going to be CaF2, solid, okay, is in equilibrium with, again, anytime they give you a KSP, it has to be a solid. Okay, that's why I knew that was a solid. And then it's going to break up into its ions, which is Ca plus 2, and then I have 2 F minuses, and that's very, very important. You can label these aqueous here, like so. You don't have to put those labels on there, honestly, because they have to be aqueous, but if you want to, you can. So that's our equation. That we definitely need. So they've told us in this problem the KSP value is 3.9 times 10 to the negative 11, and they want us to calculate the solubility. Okay, they want us to calculate the solubility. Now, since they've asked us to calculate the solubility, really what we are going to want to do is figure out the molar solubility. Okay, we're going to find X. And X is, again, the molar solubility, which I can then turn into regular solubility. Remember, regular solubility really wants its answer in grams per mole. But I'm going to get, I'm sorry, not grams per mole, but grams per liter solubility. I'm going to get it in moles per liter, and then I'll convert it. Okay, so here's what you're going to do. Set up your table around your equation. Okay, see this box that represents this solid right here? You get to cross that box off. An equilibrium table is only needed for things that are aqueous and gases, and that thing is a solid. We know it's not going to be in case SP. We really don't care about it. So any solid or pure liquid, of course, you just get to cross it off of the equilibrium table. All right, so let's start with our initial values. Initially, before we put our solid into the water, there are no ions. So for KSP problems, those two concentrations always start as 0. Start as 0. Okay, again, these are easy problems, honestly. Once you get the hang of what they're asking for, the problems are much more straightforward than even some of the equilibrium problems we've done. Okay, next line is the x's, right? So we'll put an x and an x. We bring our coefficients down, so a 1 and a 2. One side of the equation's positive, one side's negative. Well, notice we're only dealing with one side anymore, so of course make it positive. Don't make yourself deal with negatives. So 0 plus x is x. And then 0 plus 2x is 2x. I don't know, is this confusing you because I didn't draw these lines? Just put them in for you. Okay, so I know that Ca plus 2 is represented by x. I know F minus is represented by 2x. So let's go ahead. We have the KSP value given in the problem. So let's write the KSP expression. It's going to be your products. Remember, Ca plus 2, exponent is a 1. And then F minus 1 exponent is a 2, like so. And then nothing on the bottom, because our only reactant was a solid. KSP will always look like that. So I know my KSP is 3.9 times 10 to the negative 11th. Ca is represented by x. F minus is represented by 2x, and that should be squared. Okay, so then we're going to solve this. So I'm going to leave this alone for now. Okay, 2x squared, this whole part right here is the same thing as saying 4x squared, right? Don't forget to square the number and the x. So you get 4x cubed, okay? And then I'm going to divide over the 4, and we get 9.75 times 10 to the negative 12 equals x cubed. Take the cubed root of both sides, you can do that in your calculator, and you get 2.1 times 10 to the negative 4th. Now notice, we just solved for x. X is the molar solubility, okay? X is the molar solubility. So this unit is moles per liter, okay? Moles per liter of whatever this substance was. Ca, oh, sorry, oh boy, okay, hold on. There we go. For whatever we were solving for in this problem, which was CaF2, Okay, that's how many moles we have per liter of CaF2. I wanted grams per liter because the problem asks for solubility, not molar solubility. So what we're going to do is one final step here, and I'm going to get rid of the unit of moles, the CaF2, and convert it into grams. So I'm just taking my moles per liter and making it grams per liter. So for every 1 mole, a molar mass of CaF2 is 78.1. And if I multiply that out, I get a final answer of 0.016 grams per liter. So that is the solubility of CaF2. So what this is saying is that for every 1 liter, I can put 0.016 grams of that solute to dissolve. Okay, just a tiny, tiny bit. Look how small that is. We've already said, look at the KSP. Very, very small KSP, showing us this thing doesn't dissolve very readily. Okay, but that part of the problem, besides that blue part right at the end, the conversion, that part is pretty normal for what we've been doing. The issue is that you have to be able to read the problem and see what to do with it. Okay, so again, X is molar solubility. In this case, they wanted us to calculate the solubility. So we had to start by finding X and finding the molar solubility and then doing a conversion. Okay, so let's go ahead and try another problem. This one's a little different. In this one, they start by telling you the molar solubility is this. Remember, molar solubility is X. They just told you what X is. X equals 9.0 times 10 to the negative 6th. Smile huge when they tell you that. That is such a wonderful thing because this problem is going to be a lot easier due to that. And they want us to calculate KSP. So to calculate KSP, we have to know the equilibrium concentrations. So we have to start by writing our equation, which we said we are always going to have to start with doing. So LaF3 is always a solid if it's a KSP. Breaks up into La plus 3 and 3F minuses. Okay, both of those are aqueous. If you want to write them there, you can. Make a table around it. Okay, get rid of this box. We don't care anymore because it's a solid. Always are going to start with zeros because initially none of it is dissolved. Okay, initially you just have a solid. So it has to be zeros there. You put your x's, so this one will be x, this one will be 3x. We're going to make both of these positive. Okay, so our final line of adding those first two will be x and 3x. Now they want us to calculate KSP. Okay, they want us to calculate KSP, and you know that KSP is going to be equal to the concentration of your products. And then F minus, and this one has to be cubed because of the coefficient, and then there's no reactants, nothing to put on the bottom. Now they want us to find KSP. That means we need to plug in equilibrium concentrations. Remember, we already know X. Here's X right here. So X is 9.0 times 10 to the negative 6th. Well, this one just is X. So that's easy. 9.0 times 10 to the negative 6th molarity. That's your concentration for that one. And then the other one, when you multiply by 3, you get 2.7 times 10 to the negative 5th molarity. Okay, now we can plug those in. So we come over here, we say that KSP is equal to, and we do 9 times 10 to the negative 6th, and then 2.7 times 10 to the negative 5th, and that has to be cubed. Plug that in your calculator, and you calculate your KSP to be 1.8 times 10 to the negative 19th. And KSP has no unit either. Okay, and KSP has no unit either. So take a peek at that. Pretty straightforward as long as you understood what they were telling you. Okay, they were telling you the molar solubility. They were telling you X. You could just go through and solve it. And the tables are pretty simple because we've crossed off a lot of stuff and started with zeros. So the tables themselves are pretty nice. Okay, so you're going to need to rewatch any of this if you're confused about any of it. We will be practicing some problems with this, but in terms of what to do tonight, I need you to do a Socrative. So hop on Socrative right now and put in the answers to the questions that are